The nonlinearity in a model is introduced when its stiffness changes during deformation. In this lesson, we'll discuss what are the different physical factors that can potentially change the stiffness of a system and make it nonlinear. Typically, there are three main factors that can change the stiffness of a system. They are large deformations, contact nonlinearities, and material nonlinearities. There are other special cases which can trigger a change in overall stiffness, but we'll discuss them towards the end. Let's start by focusing on the first factor, which is the large deformations. As the name suggests, when a structure undergoes large deformations, it tends to introduce nonlinearity. This is because when the deformation is large enough to change the shape of the structure, it triggers changes to geometrical aspects such as wall thicknesses, area of cross-section, and may even change the direction of loading. All these changes can affect the load distribution and in turn introduce a nonlinear displacement response for an applied force. Take for instance an aluminum bar that's under tensile or compressive loading. As the load increases, the bar undergoes large deformation. In this process, its area of cross-section increases. So, as the bar deforms and the applied load continues to be distributed over a larger area. This leads to a nonlinear force displacement response, especially at large deformation. Note that the area of cross-section changes at small deformations too. So the response is nonlinear all along. But at small deformations, the change in area of cross-section is negligible. So the force displacement response at those loads can be approximated to be a linear response. Now, we may have the luxury of making approximations with a solid aluminum bar. But if we shift our focus to a similar loading in case of a thin hollow structure such as a soda can, which is made of the same aluminum material, the mechanics change. The soda can crushes under large compressive loads, and as you can notice, there's a significant change in its shape and therefore cannot be approximated as a linear response. These two examples clearly show how large deformations alone can introduce nonlinearity in the system response. Of course, there's more to it than just these two examples, and we'll discuss it in more detail in the next section. But for the current discussion, these two examples convey the message of how large deformations can make a model nonlinear. Now let's move on to the second factor, which is contact nonlinearity. To understand about contact, let's take a few steps back in time and imagine how the great pyramids of Giza in Egypt were built. The pyramids were built using over 2 million huge blocks of limestone that weigh about 25 to 80 tons each. A section of the historians believe that the construction workers used to drag these blocks from a distance over a slope to place them in their current location. Now let's imagine a group of workers who are trying to move a block from its starting place. When they start pulling it, the block may not start moving from the get-go. Instead, they continue to pull it harder until it begins to slide. Now let's look at the force displacement response of this system. Even though the workers were applying some force initially, there was no gross sliding, so the displacement is zero. Once the applied force overcomes the static frictional force of the block, it begins to slide, and if the workers are, say, moving at a constant speed, the block undergoes a displacement that's linearly increasing with the force. But even though there's a linear response, you must note that initially there was no displacement. So there's a jump in the response, and this discontinuity introduces nonlinearity. Now let's take another scenario. If the workers are dragging these blocks for, say, a mile, the frictional force of the block need not remain the same throughout this distance. It may be easier to drag it for the first quarter of the mile if the surface is wet, but it may increase over the next quarter as the water dries up and making it harder to drag the stone. So if we plot the frictional force as a function of the distance of sliding, the response is no longer linear. This is again another classic case of how contact introduces nonlinearities. There are many more industrial applications which are more relatable in present times where contacts exist and introduce nonlinearities. But not all contact types introduce nonlinearity. For instance, when two metallic parts are welded together, then they are in contact, but there is no relative motion between them. In such a case, the contact does not introduce a nonlinearity. But when the same two parts are held together by a bolted plate mechanism, then the surfaces can slide over each other to a small degree. Even this small motion can make the system nonlinear. Having said that, if this bolted joint happens to be part of a huge assembly where there is small relative motion between the parts is irrelevant, then it can be idealized as a linear contact. So the analyst must first determine whether this detail is important for their study, and based on that, plan on whether the contact should be nonlinear. Sliding is not the only source of contact nonlinearity. Loss of contact is also considered as a contact nonlinearity. Say a block that's resting on a surface is lifted upwards, it loses contact with the ground, and this is also considered as a nonlinearity as there is no longer a transfer of forces between the two. So, to sum it up, contacts between parts of an assembly can introduce nonlinearity in a model. A general recommendation to determine whether the contact is nonlinear in nature is to see if there is any relative motion possible between the two bodies that cannot be neglected, both in normal and tangential directions. If there is, then that contact introduces nonlinearity. If there isn't, then it can be approximated as a linear contact. We'll have a more detailed review of contact in a future course, but for the scope of the current section, we may end this discussion. Now moving on to the third source of nonlinearity, which is material nonlinearity. This is introduced by mechanical behavior of the specific materials used for different parts. In case of materials, we generally look at their stress-strain response to see whether the material is linear or nonlinear. Most metals tend to have a linear behavior, at least at small strains, and most soft materials such as rubbers and biological tissues tend to have a nonlinear behavior and generally undergo large deformations. In such cases, it's straightforward to pick a linear or nonlinear solver. However, a material nonlinearity in general is associated with a physical behavior, and ignoring it in the analysis may result in incorrect predictions. For instance, as mentioned earlier, most metals can be approximated to have a linear behavior at small deformations. However, if we extend this approximation to larger strains as well, then in an application such as cold forging, we will ignore the effects of metal plasticity, which introduces nonlinearity in the material behavior, and end up with incorrect results. This is because the key physics that's resulting in permanent deformation during cold forging is the metal plasticity. And assuming a linear material behavior will disregard metal plasticity, and hence our metal samples don't undergo any permanent changes in their shape, which is incorrect. Now let's take a different example. Consider the installation of a rubber O-ring and see how much internal pressure it can support. This can be done by measuring the contact pressure generated due to the deformation of the O-ring. The minimum value of contact pressure is nothing but the maximum internal pressure that can be supported by this assembly without any leakages. In the earlier case, we considered the nonlinear behavior of rubber in calculating the contact pressure. But if we approximate it as a linear measure and use the tangential stiffness for material stiffness, we can still calculate the contact pressure. But the predicted value is way different from our earlier prediction. As a result, the design engineer is either underestimating or overestimating the sealing capacity of the assembly by making a linear approximation, which is a clear case of design failure. So, in summary, if a special material behavior is of interest for a given application, or if the material is undergoing large deformations, then using the appropriate nonlinear material behavior is highly recommended. This is a very broad discussion, so we will discuss more details in a future course. Apart from these three factors, there are other aspects that may introduce nonlinearities in a model. Some instances include delamination, material failure, or snap fit assemblies. All such instances introduce a loss in stiffness which makes the model nonlinear.